Good evening, everybody. So let us start our lecture tonight, and today is October 26th, right? So let us see the course syllabus. Maybe we are in the last third of this course. We have just a few more topics, and we are discussing trees, right? In our last graph algorithm. Okay. So let's look in the course. So how was test 2? Yeah. Okay. So final exam maybe will be 50% MCQ and 50% written for the final exam. Paper. Okay, on the paper. So actually last week due to our test I missed this one, minimum spanning trees, and actually we wanted to discuss this Dijkstra and Bellman-Ford algorithms, but these are related to minimum spanning tree. As you know that we are discussing graph algorithm, right? Graph. So then the question may arise, why we are going back to tree? Actually there is a relation between graph and tree. Okay, so we know that graphs are developed from tree. Okay, the origin is tree. Okay, so let us go through quickly. So first of all we need to understand spanning tree. So a spanning tree is for a connected graph. Okay, we need for a connected graph, G set of V is set of vertices and E is set of edges. Okay, a spanning tree is a tree that actually it is a tree that is not wholly circled, and it takes one more how can I say, at least one is less than the original tree, original graph. Okay, I will come back the definition. This definition is mathematical definition. So let us give an example, then it will be easy for you to understand. Okay. This is an example. For instance, a graph is like this. This is a graph. Or let me get an easy example too. So for instance, we have a graph A, B, and C. This is a graph. Okay, so a spanning tree will be a tree that cover all vertices or nodes, okay, with minimum number of edges. Okay, so from this one we can have like A and B and C. Okay, it covers all vertices with minimum number of edges. Okay, or we can have like B and C and A. So there is no connection between A and C. Okay, this is a different one, or we can have another one like A and C are connected and B are connected. Not A and B are not connected. Okay, this is a okay, this is a spanning tree. Okay, so I'm coming with minimum spanning tree better later. So spanning tree. Now let us see the example. For a connected graph G, V is the vertices here, A, B and C are the vertices, and E are the edges. How many edges? We have 3 edges, 1, 2 and 3. Okay, a spanning tree is a tree with a new set of vertices, okay, and new set of edges. Actually vertices should be same, it should be same. B and B dash should be same. Okay, where such that B dash is a improper or equal subset to B, and E dash is improper or equal, actually it should be a proper subset. It should be like this, not this equal. Okay, and this is true, so B should be B dash should be B, and it forms a tree and without any cycle. Okay, so the condition is that actually it is hidden. If we say that if we take one more if we take this improper subset, then definitely it will not create a cycle. If we take our set E dash, A is of new set of edges, if it is a proper subset, that means it is not equal to E, then definitely we have to at least one edge less than E. So this is a spanning tree. So for a tree, for a given graph, there are multiple spanning trees. Okay, in general, so the how many spanning trees? So number of spanning trees is the combination. You understand combination, right? So here number of edges will come here, set of edges, and then here will be V minus 1, and then minus number of cycles. If there are cycles in a graph, then cycles maybe number of cycles need to be reduced, subtracted, to find how many number of spanning trees. So for instance, for this one, okay, so our edges, set of edges, number of set of edges 3, right? So it's a 3, and then C, and vertex will be 3, right? 3 minus 1 is 2, so 3, so 3C2, okay, equal to factorial of 3 divided by factorial of 2 into factorial of 3 minus 2, right? So that is factorial of 3 into factorial of 2 divided by factorial of 2 into 1 factorial of 1 equal to 1, that means equal to 3. So there will be 3, 1, 1, 2 and 3 different spanning trees. So similarly, if I have a spanning tree like so D is here, if I have another graph like this, if I have another one more node D, okay, so then it has a cycle, right? In that case we will consider that this is a cycle. So in that case, how many you can do it, okay? So how many spanning trees will we have? So here how many edges? 1, 2, 3, 4, right? 4, and then C, number of vertices equal to 4, right? Then 4 minus 1 equal to 3, and minus how many cycles over here? 1. So equal to, actually it can be easily calculated by this way: 3 into factorial of 2 divided by factorial of 2 equal to 3. It can be easily calculated this. So here this means 4 into factorial of 3 and then factorial of 3 minus 1. This will be 4, this one cross out, will be 4 minus 1 equal to 3. So this is, you can try this one, there will be 3 total spanning number of spanning tree. Okay. Has anyone any question about spanning tree? So a spanning tree is derived from a graph that covers all vertices, okay, but it never makes a cycle. Graph may have cycle, a graph may have cycle, okay. A spanning tree does not have a cycle. So for instance, you can have a graph, for instance, like this. I may have a graph like this, A, B, C and D. It is already circular, okay. And then how many you can try, okay, how many by this formula. And then I have like this, I may have this, okay. So this is called A's, right? If there is no direction, this arrow sign, this unit then bidirectional. So there is a path between C to B and B to C. But if you see that is an arrow sign like this, then that means there is a path only from C to B, no path from directly from B to C. Okay, it can be like this, or it can be like this. Okay, so now let us go. So now understand what is a spanning tree. What are spanning trees? So there are multiple spanning trees, right? Okay. So now the concept of minimum spanning trees. Then how many minimum spanning trees can be? What is minimum? Minimum spanning tree if there is a weighted graph. For instance, for our graph, like a graph is like, if our graph is like this, A, B, C, D, like this, okay? Let me make it clear. If my graph is A, B, C, and D, okay, A to B is 2, right? B to C is 1. A to C is 2 or 3. Do you see 2 or 3? Whatever, it's 3 maybe 4. Whatever, this is not a matter. These are the weight. Weight means, for instance, it may be it may be cost or loss, okay, or in case of profit, okay, in case of profit, this may be profit, okay, or this may be toll or taxes. So whatever, sometimes we can say optimum. So minimum, there are minimum spanning trees. So if we consider that these value are for cost or loss, okay, then we will want to minimize our loss, right? For a business, we want to minimize our loss. So a minimum spanning tree is a spanning tree that has minimum cost. This value are minimum cost. So you can see that, you can try that. There will be about 20 trees, spanning trees for this one, okay. And for this one, so there are these two, 1 and 2, these will be minimum spanning trees. It depends on situation. There may have multiple, one or more, at least there will be one minimum spanning tree. For same graph, there may have more than one spanning trees for this one, for instance. And we will see a few more in our example. Okay, so minimum spanning tree is a spanning tree that has minimum cost or minimum loss. For instance, we can consider that maximum spanning tree. So for instance, profit. In case of profit, right, we want to make profit for a business, right, for gain. If it is gain or profit, then we can say that maximum spanning tree. That will give us maximum profit. Okay. Okay. So for a graph like this, a simple graph, it can be we can figure out, or we can find out minimum. So we can sometimes say MST, minimum spanning tree. Okay, we can find MST, minimum spanning tree, for a small or simple graph. But how about for a large graph? Like we discussed GPS system. Our GPS system works graphs, right, inside. So it works. It finds minimum distance or shortest distance, shortest path. Okay, so there are many routes and then many possible ways. So it is not possible for a human being to quickly figure out all possible minimum spanning trees, right? So this is why there are some algorithms. So inside GPS system and then like that kind of application, they use spanning like minimum spanning trees algorithms. There are some well-known algorithms. We will see a few. We will see a few this week. Okay, in this chapter. So we know that how is the strategy to find a minimum spanning tree. We expand the tree, right? We added the for any tree we insert edges, we add new edges, but we just avoid cycle, not to make a cycle. That's it. We have to cover all edges, all vertices or all nodes, but we need to be careful so that we do not make a cycle. A spanning tree cannot have a cycle, right? That is the restriction, if you remember. That will be good. Okay. So we will see that there are some algorithms that repeat actually v minus 1 times, vertices minus 1 time. If there are two types of algorithm, we will come this later. One is greedy algorithm, another is called dynamic algorithm. So let us think that, okay, and let us give an example. For instance, this. Okay. Sometimes, for instance, like this kind of graph, the weight may be positive or negative. Okay. For instance, this is a business graph. Okay. That means, for instance, negative, if positive value means you are making profit. Okay, and negative value means you are losing money. Sometimes in a business you can gain money, you can lose money, right? Okay. So, for instance, we may have negative is weight. This in general we call it weight. Okay, if we have negative is, then we have two other algorithms, that is called Dijkstra algorithm and Bellman-Ford algorithm. Okay, but if all the weights are positive, that are simple. Okay, so let us start with simple graphs. Okay, and that have positive weights. So all edges are positive. If any weight is negative, then we have another algorithm. Okay, tonight we will consider all the algorithms that are positive. So there are two popular algorithms. One is called Prim's algorithm, and another is called Kruskal algorithm. Okay. So the concept is that Prim's algorithms, it builds a tree incrementally. Okay, and Kruskal algorithm, it takes like some books say something, it says that it makes a forest like if to finish it. I will come with the examples so that we will see that. Okay, so let us see that. We will come to the algorithm later, but let us see an example first, illustrate. It's an example. So our strategy is always maintain a tree. Okay, and what we are doing, we are developing, we are finding minimum spanning tree, right? Minimum spanning tree or trees. There may have only one spanning tree, minimum MST, or we have multiple MST. Okay, so the concept is that it can start from any vertex. Okay, the other algorithms, Dijkstra algorithm and Bellman-Ford algorithm, there says if we have a given starting point. But here, for instance, we consider that we do not have any restriction that we have to start from here, because we want to find a minimum spanning tree, right? The definition of, according to the definition of minimum spanning tree, it covers all vertices, right? So from wherever I start, it not a matter. Our matter is that, condition is that we need to cover all vertices, and another condition is that there will be no cycle. Okay. There will be no cycle, and there will be no vertex missing. So apparently it says that we can start from any point, right? So the Prism algorithm says is that is always maintain a tree. Okay, and then where should you start from? Since we are developing a minimum spanning tree, so we should start from an edge that is minimum value. So I can start from 1. This is between okay, the two things over here, don't be misled. The circle, the number within circle, these are a vertex. Okay, vertex number 1, vertex number 2, vertex number 3, vertex number 4, vertex number 5, vertex number 6. And the number without cycle, these are weight. Okay, sometimes you will see A, B, C, D. Instead of this, you can say A, B, C, D, E. It's better to see. Okay, so now if you consider, we can take, so the Prism algorithm, it says that Prim's algorithm, it says that start from a point that is minimum age, okay, minimum value, and then grow a tree. So where can we start? Either we can start from here, this age, or we can start from this age, or we can start from this age. There is no restriction. Okay, so let us start one way, then we can go another way. So let us start from this age. This is minimum value, right? Okay, so we start from this one. So then initially our vertex was empty. Okay, our setup, so we started from this one. We started from this vertex 1. Yes. And then age was initially empty, then we took this one, 1, 2, 3. So we took 1, 2, 3. So we take vertex 1 and 3 vertex, and then the age we got. So ages are defined within parentheses over here. You see that within parentheses. This means that there is a line, there is a connection between 1 to 3. Okay, so whenever we take a vertices 1 and 3, then we got age 1, 2, 3, right? So then which one we should take? So we have this one, right? Then which one we should take? Our condition is that we will maintain a tree, right? A tree, in a tree all branches are connected, right? In a tree we will not find a branch is broken. That branch is gone. If this branch is broken, that branch is gone. Okay, so a tree, so let us copy this one. So this is our goal. What is our goal? We will always maintain a tree, right? So if we want to maintain a tree, what is the next minimum spanning tree we can consider? So this is the one, like we have, so from 1 and 3. So look at the vertex connected with, look at the edges connected with vertices 1 and 3. So we have 10, we have 8, we have 5, we have 3. So minimum is 3, right? So then we will take 3. So then we will take 3, and then when we will add 4, right? Our new vertex will be added 4, and then we will go 3 to 4. So 1 to 3 and then 3 to 4. See that this sequence means 1 to 3 and then 3 to 4. So now we got this tree, right? So then again we need to, what is our strategy? We need to maintain, always maintain a tree, right? So what are the other edges? We will see that are related to 1, 3 and 4, but we cannot make any cycle. So we cannot take 5, right? It will make a cycle, right? Okay, so then what we can, so we can consider 4, 6, 8, 10. We cannot consider 5 here, right? So what is the minimum one? 4, 6, 8 and 10. 4, right? So we will take the vertex 5. So next step we will go 4 to 5, right? So next vertex will be 4 to 5, and then we will add this one. Okay, so then next vertex will be 4 to 5. So now at this point we will see then what else we will connect. Okay, so now we have this one, 1, 2 and 8 and 10, right? Take the minimum. Okay, so then 1, 2, 8 and 10. So 1 is the minimum, right? So then we will include 5 to 2. Then we will include 5 to 2. Then in the next iteration we will consider 1, this 2 is related to 5, right? 1, 2, 8 and 10. Which is the minimum value? 2, right? This one, right? 1, right? 2 to 6. Then 2 to 6. And then now let us see that this is our path. So this is our minimum spanning tree. So this is our minimum spanning tree. So our minimum spanning tree goes this way. One, 2, 3. So we got weight 1, and then 3 to 4 we got weight 3. Then 1 plus 3, 4, and then 4 plus 4, 8. 8 plus 1, 9. 9 plus 1, 10. Okay, so this is one way, right? So initially that we could start, also we could start other way. At the beginning, okay, instead of this way, instead of starting from 1 to 3, okay, instead of starting from here to here to here to here, we could start other way. For instance, we could take either 6, this is the minimum, right? 2 to 5, 2 to 5 or 2 to 6. So let us take 2 to 6. So let us take 2 to 6. Okay, then which else we have to consider? Then 2 to 5 1 and 6 to 5 2, then 2 to 1 10, and then 8. We have to take the minimum one. Which one is the minimum? This one is the minimum, right? So we then first one, then take this one. After that, what is your consideration? 2, 4, 8, and 10. Then which one we will take? We have 2, right? This is 2. We have this is 8. So related, we will see all related edges. This is, we can consider this or this or this or this. So which one is minimum? Minimum is 2, but we cannot take these 2, right? Why cannot take these 2? Because it will make a circle, right? It will make a circle. So we avoid 2, right? 2 is disqualified. So this is the only way we can consider 4. Now when we come to 4, then we have path 3 and 5. Definitely 3 is the way, right? And then when we come to 3, then we have path already, so we cannot go 6, right? If we go, let us see. So 3, we have 1 and 8 and maybe 6. So then definitely 1 is the minimum, right? And then now 1, we come at 1. So one thing that we already cover all vertices. This is done. Or you will see that we cannot cover this because this will make a circle and this will make a circle. Even this will not make a circle, this one, but we already covered all. Also, if we take this one, then it will make a circle. We will connect. And according to our spanning tree, it cannot be a circular, right? So now it is done. For any way, so then if you take this way, then you will get same weight. So we say that we can draw different way, but the resultant final cost will be same. Does anyone has any question? Yes.
So why can't the values be negative? Why can't the weights be negative?
We will discuss for negative weight later. There are other formulas. For Prism algorithm, it does not consider negative. It is not applicable for negative weight.
But, like, why not? Because like if you had a node that had like 1 and -1, like -1 is less, right? So you just take -1.
There are two other algorithms. Dijkstra algorithm and another dynamic algorithm is called Bell-Mulford algorithm that takes negative. I understand your question is a good question, but maybe the book has the reason why Prism frames algorithm cannot consider negative. We can search for the book, but so far I know that Prim's algorithm and Kruskal algorithm they are applicable only for positive. Okay. So it's simple, right? The strategy is that we will always maintain a tree, spanning tree, right? Okay. Now there is another algorithm. It is called. So now we can come to the Prism algorithms. You can come to the algorithm. This is the algorithm in pseudocode format. Okay. So the cost will be big O m plus n. Okay, it's m plus n log n. M plus n log n. We will come this later. Let us discuss both algorithms. And then the Kruskal algorithms. So it takes it always okay. So select edges of minimum edges. Okay, the rule of the technique is that select edges in order of increasing cost. That means starting from edges that are minimum cost. Include the edges that are minimum cost. Okay. So select edges of minimum cost and accept an edge to expand the tree, okay, if it does not cause a cycle. Same condition over here, so that, okay, the Prim's algorithm said that start with any point, okay, with a minimum point, and maintain a tree, maintain a path, okay, minimum spanning tree, minimum path. But here it says take always minimum cost edge or optimum. We can say optimum, for instance, in order to solve if we make profit, then optimum. Okay, so let us, for instance, this is minimum is fine, or optimum, you can whatever you say. So this is the algorithm. I'm coming back to algorithm later. So let us see some example. So let us do this. So what is our technique? Our technique is that take edges of minimum cost but avoid cycle. In short, we can say this. This is our technique, okay? So which edges have minimum? Okay, technique is the always select minimum edge but do not make a cycle or something. Okay, so which edges are minimum? Okay, we see that there are 3 edges that are minimum, right? Okay, so then which one will you take? Any one. Okay, so we can take this one first, or we can take this one first. We can take, so in an algorithm or a program, it goes step by step, one statement by another one statement, right? So you cannot take 2 statements together. So you have to either take this one first, or this one first, or this one first. Either one. Okay, so for instance, first one I took this one, and maybe the second one I took this one. Okay, or first I take this one, second is I take this one. I don't need to maintain a tree over there. Okay, Prim's algorithm that maintain a tree always, but here it does not maintain a tree. It says that always select minimum edges. Okay, so I select this one, this edge. Okay, and Prim's algorithm that selected vertices, right? And here it selected, that selected Prim's algorithm selected both vertices and related edges. But here it says it selected edges, then vertices come later. But Prim's algorithm, they selected vertices first, then edges come. And here we are selecting edges first, then vertices are coming. So this one we will select. Then what else we have to select? What is the minimum one that does not make a cycle? This one, right? So we make this one. Then what is the minimum one we can select? Can we select this 5 to 6? No, because the condition is that do not make a cycle. We cannot select this one, right? Although it is minimum. The reason is that it will make a cycle. So what else we can select? We have option, we have 4, then 6, 8, 10, 5, 3, then which one will select? Huh? 3. You said it does not need to maintain 3, but we will select the minimum. Third one, right? Okay, fourth one. Then what else we need to select? We have 5, 4, 6, 8, 10. So if we select 4, will there be a cycle? No. So then we can select 4. So the cost is 1 plus 1, 2 plus 4, 6 plus 10, 4, 10. Either you use Prim's algorithm or Kruskal algorithm, it will give you same minimum weight. Okay, but the complexity may be different. Does anyone has a question? Now if we go back to algorithm, so algorithm is, if you understand, then you can find the algorithm. How many times we need to repeat? We need to repeat the number of vertices minus 1 time. If there are 5 vertices, we need to repeat 4 times. The loop will go 4. If there are 10 vertices, we need to go 9 iterations. So these are the algorithm. Okay, so the algorithm is, this algorithm, it says make a forest. Forest means the tree is connected or adjacent. Okay, so now you can go through the steps. This is according to algorithm, these are the steps. How do we connect? You can connect in different order. Okay, so Kruskal algorithms, it has for the running time m log m. M is the number of edges and n is the number of vertices. Okay, for a for the worst case means if the graph is fully connected, okay, then there will be more edges than vertices. Okay, in that case m, in general it is m log n. Okay, or if there is a fully connected graph, then we can say m log m, and m and n will be maybe pretty same for a graph, but in the worst case this will be. Okay, and Prim's algorithm takes m plus n log n. Okay, in that case Kruskal algorithms runs better, but in the worst case Kruskal algorithm run in n squared. N squared means what is n squared? Actually, if, let me write it down. Write it now, please. For a connected graph of n nodes, there may have n into n minus 1 by 2 edges. This is the formula. In his book you can find this. Okay, So for a graph, connected graph A, B, and C, how many edges you can have? N here equal to of n nodes or n vertices. So n equal to 3. 3 into 3 minus 1 divided by 2 equal to 3. So there are 3 edges here, 1 to 3 edges. So if a connected graph is like this, A, B, C, D, and if I have like this, so how many nodes it can have? How many edges it can have? Why is not working? Then in that case, we may have n equal to 4 over here, right? 4 vertices. 4 into 3 divided by 2. That means 12 divided by 2 equal to 6 vertices, 6 edges. You see that 1, 2, 3, 4, 5, 6, maximum 6 edges. So in that case, so big O of n into n minus 1 divided by 2 equal to big O n squared. This is why they said big O n squared. So this is the formula, okay, to find how many edges, maximum number of edges. For the worst case is the maximum number of cases, right? Does anyone have any question? Okay. So now let us do some activities. First one, find the minimum spanning tree for this one. What does it do? Draw the minimum spanning tree for this one. It can have one tree, one minimum MST, or it can have more than one. Just draw it. Only one, or there can
Oh, you want all of it? Because there's 3 variations.
Okay, let us see.
Okay.
If there are multiple, then I figure out. I believe there are more. How many there?
There are a total of 3. Because you can swap these and then do CD instead of DC. And those all have been
How many
crossed.
there? I got 2.
too. You can, the last one, you have BC and you have DC for conflicting edge. So you get 2 off of that, and then you can swap DE and AD. And so you get 1 off of that. So it's all 3.
So you can say 2 to ADDE, then 2 to, then 3, then AB, and then you can take either B or C or D or C.
Yeah.
I mean, those are the same tree though. The A and B.
No, if you take
Order's different.
The order is different, but for a tree it doesn't matter.
Yeah, but that's the point, is that using Kershals and using Prims, you get different trees, but they equal the same because they're all minimum span, but they're different orders.
order is not a matter.
Then-
Whatever say the tree needs to be different.
Yeah, precisely, which would mean
So
that it matters.
the tree itself, the two trees themselves are the same. The order you get them might be different, but since it's just asking for the tree, you only need two.
Order doesn't matter unless then all the spanning trees are always gonna be 11. And what I'm telling you is there are 3 conceptions of that tree that all equal the same minimum span.
But two of them are different trees.
I see like 2.
I mean-
What is the third one? Can you please
Yeah,
draw
so
it over here?
Yeah, well, I mean, then
Draw.
if you want them.
Can you please draw it?
Sure.
Draw it, please.
I think
Two,
if
two,
I
four.
understand what he's
Yeah.
saying is that
Yeah, what I'm saying is that the
so
swap.
if you go E to D first and then A to D, that's different from if you go A to D first and then E to D.
That is not a matter.
Okay, then there would only be 2.
Yes.
Yeah,
That's 2.
that was just a clarification.
So in the final part, so it's a minimum spanning tree, we will measure the minimum weight, right?
Mm-hmm.
So the weight, whatever if you add 2 plus 3, 5, 5 plus, 3 plus 2, 5, right? It will not tell you whether it is 2 plus 3 or 3 plus 2. There should be 2. I see. Since still do you see third one?
No, there's 2.
Yeah, 2. I see.
Yeah.
You got 2? Oh, 2. Drop it.
Yeah, that's just because the order doesn't matter. Because I would say if you use Prims versus Kershals, you can get 2 different trees.
No, if you get 2 different
Yeah.
weight, then there should not be. Weight should be same.
Yeah.
Weight should be same. Weight should be, what is the weight?
11.
2 plus 2, 4. 4 plus 3, 7. 7 plus 4, 11. Weight should be 11, but 3 has 2 different trees, right?
Yes.
Okay. Has anyone got different weight other than 11?
I just kept that.
You got it? You got 11? You got 2? Who did not get 2? There will be 2 different minimum spanning trees. Who could not find 2? Anyone? So everyone got 2?
I couldn't find the other one.
You couldn't find another one? Okay. So, one will be, first of all, so we need to take either this one, these 2 or these 2, either A to D. So first of all, either this one, right? Or this one, whatever you take, no problem. Okay, then it is this connecting these 3, right? And then now you have 4, 4 and 3. So which one you will take? 3, right? 3. Now you have one node left, right? So then you can connect this node either with 4 or either with D, or you can either DC or BC. So if you connect DC, then it will be one graph, and either if you take BC, then it will be another graph. Not graph, sorry, tree. You understand? I got it? So here the variation will be this one, this part. Okay. So sometime you may be given a spanning tree, okay, and then maybe some weight may be hidden, okay, or for instance, let us see another activity. Okay, for this one, let us see this activity. If the following graph forms a minimum spanning tree, okay, what will be the minimum value of x and y? What will be the minimum value for x and y? X and y can any value, have any value, 100, 200, 400, whatever value, okay, but we are looking for minimum value. Draw the minimum spanning tree, then you will find out. First draw it. So the condition is this, says that it will be a minimum form the minimum spanning tree. Form it first, then you will get it clear.
Is zero multiple values, or is it just one?
I've never seen zero. Wait.
Okay.
Minimum should be 1. Zero should be minimum. Okay, so let us. We have a few more minutes there. So, so let us see that. Let us form a minimum spanning tree first. Okay. So how can I form the minimum tree? So for this node for A, B, and C, this part, we cannot take all 3 nodes, right? We can take maximum 2 nodes, right? Okay, so we can take either one, this, okay, either one, for instance, either this one or this one or this one. Okay, for instance, let us think that it is 2. Think it is 2, for instance. Then if it's 2, then we can take either this one or this one or this one. This is right. Either these edges and these edges. 2 of these 3 edges. Okay. But for this case, if we have 2, then there will be a collision because which one you will take? I think in that case, actually, let me see, 2 and then 2. And in that case, skip this one. 2. I think it needs to be 2, minimum 2, for x minimum 2. Okay. But if I am given, for instance, it is minimum 2, a path, already if it's given a path like this. If it is given a minimum spanning tree like this, then it is easy, right? So here, like if you are given this one, right? So then, for instance, let us try understand with a given minimum spanning tree. For instance, if my minimum spanning tree is like this, if it is given, for instance, then what will be the value? So in that case, this will be 3, right? Minimum value will be 3, right? If it is not, if it is less than 3 or equal to less than 2 or equal to 2, then I could take this one. But my minimum, my spanning tree says that I cannot take this one, right? So in that case, it is greater than 2, right? Maybe 3. Greater than 2 means minimum. If we say integer value, then 3, right? Minimum value is greater than 2, that means maybe 3. Okay, and then y, for instance, over here, y, if you take this one, right? So after you form this one, right, you are going to this path. So the y less than this 4, right? Y needs to be less than this 4 but greater than this 2, right? Right? So here y greater than 2, maybe 3, consider this is 3, okay, and in that case you are given 4, so we need to x and y, okay. But another thing is that we don't know who is on us drawn first, right? So in that case, for instance, if this is drawn first, this is taken first, right? So in that case, that may be the minimum one, right? In that case 1, right? In that case 1. So minimum value will be 1, right? In that case 1. So if we consider that we don't know that which way it was created, but if I am given a direction, for instance, here to here to here to here, then y will be minimum 3, okay, and x will be also minimum 3, okay, and but if I don't know which direction is if it uses cross-call algorithm, right? It comes this way, in this way, in this way, then this way. So then it can be 1 also. It can be 1. Okay. There are some problems for advanced level algorithm course. There are some problems like this. Okay. But I'm not going to that's not complicated, but for simple, let us see another one. Okay. So let me make it simple. I can make it like this is our minimum spanning tree. Okay. So what is the minimum value for P and Q? Yes.
4 and 6.
For P, yes, it needs to be greater than 3, right? Okay, so P is greater than 3. So if we consider integer value, then 4, right? Or we can say P is greater than 3. Okay. So we are avoiding this one, right? And then Q, let me guess someone else. Look at me. Yeah.
Does order matter?
Order. Okay. So let us make order. First, this one, 1,
I would say no.
2, 3.
You should be able to evaluate a spinning tree with controls.
Order, I think even if it's in order to 1, I think order is not a matter over here in this case.
It does.
If it does,
Yeah, because if you use like Kershaw's and you end on C, the only option you would have would be like to go to.
for instance, if it's cross call, right? If you want, for instance, 1, right?
Yeah.
Then you can you're taking this one, right? And then you are taking this one, and then you are taking this one, and then you are taking this one. Okay, let us make it Prim's algorithm.
Yeah.
Like that, let us make it Prim's algorithm. So okay, so Prim's. So if you want Prim's algorithm, then what is the value? So it's order. So here, so in that case, oh, okay. So maybe the original was like this side. C2, this one. Okay. So here, I cannot have 5. Then it can be 4. Maximum value can be 4. We are saying minimum value, right? Minimum value can be 1. It can be 2. It can be 3.
Yep.
Right?
Yep.
It can be maximum value can be 4, right?
Yep.
Maximum value for the P, I can get Q for I can get maximum value. Okay. So okay. So in order to maintain my question. So we need to do this way.
Yes.
If I have this one. Okay. So then what will be the minimum? This in this case we can get the minimum value for Q. I'm gonna ask someone else, please. Never mind. You can write it down for me. Right?
I don't know. No.
So I'm asking what is the minimum value for Q?
Would the minimum have to be at least 4 for it? Just because.
No. If you take 4, then I could take A and B. Then why I'm getting 5? It needs to be greater than 5, right? Understand? It needs to be greater than 5. Then we can avoid it. Right?
That's the only minimum spanning tree in this example.
I don't know. Let's see. So only minimum spanning tree. First of all, we need to find minimum spanning tree. We have good question here. So I do not think only minimum spanning tree. See, it is in there. Minimum spanning tree. So 1 plus 2, 3. 3 plus 4, 7. 7 plus 5, 12. Another way. So the question says if it is a minimum spanning tree, then it needs for integer value it needs less than at least 6. Okay, or greater than 5. Oh, sorry, we are at the end. Give me a few more minutes, please. So in our next lecture, we will discuss there are few more algorithms. The 2 popular algorithms. One, give me 1 more minute, please. So for these cases, minimum cases, we do not have any fixed starting point. So we said we can start from any any node, right? Any vertex, right? But if you are given a fixed starting point, if I have my starting point and then destination, source and destination, that for instance in GPS system, right? We give a starting address and ending address, source and destination, right? So there are two other popular algorithms. One is called Dijkstra algorithm, another is called Bellman-Ford algorithm. So in our next lecture we will see these two algorithms, okay? Now give me 2 more minutes please, let me give my attendance. So does anyone has any question? Okay, thank you.